Contrary to what was predicted at the end of the last part, today we only create the full add. The reason for this is the amount of mathematics we will need to derive it. So let's get started then. Today we'll look at adding two numbers. Since our processor should only add 4-bit numbers, we define the addends and the sum accordingly. Now we calculate z accordingly and combine equal powers. We calculate a and decompose the sum into two possible bits. We recalculate z and summarize again. Now we replace all summanders in the second position with b and also insert this into z. We proceed in the same way with the other two places. At the end we notice that z is now larger than it should be. We now add the extension accordingly. As we saw, we need an addition of 3 bits for all digits except the first. We define these and break them down into two 2-bit additions and solve them accordingly. This is how we get to this equation. Now we use our knowledge about the half adder and generate the corresponding logical equations. Now let's simplify T2 according to the known rules. In the end we get 0, which makes sense. Because if T2 were ever 1, that would mean that adding 3 ones would make 4 or more. We know that's not the case. Now let's look at the half-adding of the last part. We will now define this as a function accordingly. Now we replace the logical operations with the functions of the half-adder. We come up with the following equations. Now we build the circuit accordingly. Now let's create the full adder component. We use this command for this. As always, we will now adapt the calculate method and also create a fast method. The remaining adjustments will be made as usual and will no longer be displayed from now on. At the end we create the circuit with the new component and test it. In the next video we will create a 4-bit adder from the full adder.